Propelling a massive metal tube miles above the Earth requires thousands of complex mechanical parts to operate in unison. On paper, it is a high-stakes mechanical challenge. Yet commercial aviation stands as the safest form of transportation created, and the Airbus A350 exemplifies how that record is maintained. Since entering commercial service in 2015, this aircraft has completed millions of flight hours without a single fatal passenger accident. Since the A350 isn't magic, how exactly do engineers design a machine capable of driving the probability of mechanical failure as close to zero as possible? Safety at this scale is the result of taking every historical threat to flight and turning it into a solvable engineering problem. The first major threat any aircraft faces is the environment itself. Continuous structural stress, extreme temperature shifts, and moisture eventually lead to metal fatigue and corrosion in traditional materials. To address this, more than half of the A350 is built from carbon fiber reinforced composite materials rather than aluminum. These composites resist structural stress and fatigue much better than metal. The lighter frame also means the aircraft can carry more fuel or passengers with less strain on the airframe. By changing the physical anatomy of the plane, designers removed an entire category of historical structural threats before the aircraft ever leaves the ground. The next vulnerability is human error. Even expert pilots can make manual mistakes that lead to dangerous aerodynamic stalls or excessive banking. The technological solution is a digital flight control system known as fly-by-wire. In this system, powerful computers sit between the pilot and control surfaces. When a pilot moves the stick, computers calculate the stress it places on the aircraft. If a command pushes past safe limits, the system restricts the input, keeping the plane within design parameters. The A350 is engineered to protect itself from pilots, functioning as a persistent digital safety net that bridges the gap between human input and physics. But what happens when a physical part simply breaks mid-flight? This is where the principle of redundancy takes over, starting with the twin Rolls-Royce Trent XWB engines. Modern twin-engine aircraft are designed so that if one engine fails, the plane is certified to fly and land safely using only the remaining engine. This concept of layered backups is repeated for every critical function. The A350 runs parallel electrical circuits, hydraulic lines, and navigational equipment throughout the entire airframe. If any one of these primary systems fails, a secondary backup immediately and automatically restores the connection. Through this extreme redundancy, a mechanical failure is shifted from a potential crisis to a manageable technical event. The machine is only half of the safety equation. The rest of the work happens entirely off the aircraft. During flight, sensors monitor thousands of internal components, beaming real-time performance data to maintenance teams on the ground. This predictive data allows engineers to identify microscopic anomalies and replace components long before they have the chance to develop into emergencies. Despite the heavy automation, the human pilot remains a central failsafe in the system. Airline crews spend countless hours in motion simulators, drilling severe emergencies, like bird strikes or total hydraulic failures, that they will likely never encounter in their entire careers. This safety culture applies across the industry. Other modern jets, like the Boeing 787, maintain outstanding records when operated with these same rigorous standards. Aviation safety isn't just about building a strong machine. It is a network where technology, strict maintenance, and human expertise interact to manage risk at a scale few other industries can match.